Good afternoon. Welcome to Chem 400 lecture today. We're on chapter 11 now. So glad you decided to join me on the day before Thanksgiving, and I forget to say it at the end. I do hope you all have a good Thanksgiving, free from too much chemistry. Or at least studying for it. Watch out for that turkey. You never know how it's going to affect your bodily chemistry. We were talking about intermolecular forces, and I know we went through this slide already, but I want to put it back up here and say that this is listed from weakest to strongest, and we will later, and certainly on the chapter 11 homework, but later in this lecture, be asking you to rank intermolecular forces, and generally you'll go from weakest to strongest. When you do, something that only has, well, let's do this, only has or has as its dominant intermolecular force dipole forces will tend to have weaker intermolecular forces than something that has as its dominant intermolecular force hydrogen bonding. And what we can say then is, if hydrogen bonding, if the intermolecular forces are stronger, then whenever it's stronger, we'll have a higher boiling point, higher melting point, higher surface tension, higher viscosity on down to 6, actually. And then vapor pressure, we said if it's got stronger intermolecular forces, it will have a lower vapor pressure. And we said solubility, well, solubility, the only time we use, the only intermolecular force we generally talk about for solubility is ion dipole forces. Anyway, we'll talk more about that. But the only time you ever give ion dipole forces as an answer will be some questions for solubility. That is just true. Okay. So now I'd like to talk about what these intermolecular forces are by drawing you pictures of them. So pictures and description of dispersion forces, also called LDF. LDF between helium atoms, and this will be only 2 electrons per atom. And so this will be one of the simpler cases to draw. Here's a helium atom. It's got its nucleus, it's got 2 electrons in the 1s orbital. And although electrons exist as probabilities, and those probabilities are scattered equally around the atom, I am now going to draw the electrons as if they are in one place. And so, for example, the 2 electrons for an instant are on this side of the molecule, this side of the atom. And so, in addition to a picture, I'm going to write some words here, and it says, for 1 over 10 to the 15th seconds, both electrons in a helium atom are on the left-hand side of the atom. And I'm going to write this all here because there's going to be another helium atom here in a second. Both electrons are on the same side of the atom, creating an instantaneous dipole. Creating an instantaneous dipole. And last time I told you that dispersion forces, LDF, are intermolecular forces based on instantaneous dipoles. And so that's what we're doing here. And we can draw this instantaneous dipole. So if these 2 are the electrons, then this side of the atom is going to be partially negative, while the other side of the atom is going to be partially positive. for an instant. And what is an instant? It is 1 over 10 to the 15th, 1/5 seconds. Which is a femtosecond, if you're wondering, keeping track of your powers of 10. For a femtosecond, both electrons are on the same side of the atom, creating an instantaneous dipole. Dot, 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 the story's not over. We know the story's not over because intermolecular forces are always forces between two different things, and we don't have a second thing yet. That second thing is another helium atom. And this time, I'm going to draw it. And again, this is a simplified picture, but I'm going to draw it roughly without a dipole, meaning the electrons are sort of in the middle. And those electrons are attracted to the instantaneous dipole here because electrons are negative, and this side of the atom is positive. So dot, 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 and I guess I have a lot of space up here, dot, 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 inducing a dipole in the neighboring helium atom. And so over here, when the electrons move, now we have a partial negative and a partial positive there. LDF is the attraction, or I guess LDF, London Dispersion Forces, are the attraction between the instantaneous dipole and the induced dipole. LDF are the attractions between the instantaneous dipole and the induced dipole. The attractions between the instantaneous dipole and the induced dipole. And maybe you're starting to see why these are the weakest of the intermolecular forces, because a femtosecond, sure, that's a short time to have a dipole. It induces a dipole. These are partial. They are not permanent charges. They're temporary or instantaneous charges. Questions about this? Because I think this is one of the questions on your Chapter 11 homework, is draw me dispersion forces. Okay. There's more to it, but the next thing we have to know about LDF is going to be illustrated here by argon. Argon has 18 electrons, and so LDF scale with the number of electrons. And scale just means as the number of electrons increases, the LDF increase. That's just a restatement of that. And so another picture is uses this concept of polarizability. Polarizability is going to be, instead of drawing this picture here for argon, we'll draw an actual deformed electron cloud. And now let's say it looks something like this. So this is now the electron cloud showing more of the electrons on the left. And this is constantly moving because there are random fluctuations in it. That's what we're dealing with here, is random fluctuations. But it's the same idea. With more of the electrons being on the left, there's a partial negative charge here, partial positive. That's then, well, I think the picture to draw here is actually of the intermolecular force. So inducing a dipole here, so instantaneous dipole, induced dipole. And there's an attraction between them. So either of these pictures are fine ways of drawing. But the idea is the electrons sloshing around atoms are not always equal. There are slight fluctuations. Questions about that? If you must know, LDF are my favorite intermolecular force for two reasons. One, even though they're the weakest, they do on a per atom basis or a per interaction basis, you get enough electrons together and they rule the world, or at least they become bigger. And the other is that when I was in grad school, one of my papers was about calculating London dispersion forces. And that was fun too. Okay, so that's LDF. More about dispersion forces. So first off, all particles have dispersion forces. So they're ubiquitous. Everybody has them. For nonpolar molecules, LDF are the only intermolecular force. So as we classify intermolecular forces, you have to know what is a nonpolar molecule, and that LDF are the only intermolecular force. Like I said, LDF scale with the size of the particle. For example, the noble gases. These are atoms. And what we're showing here is not just the number of electrons, but the way it's typically done is you just look at the molar mass. So number of electron increases as the molar mass increases. So we usually look at molar mass. So we usually look at molar mass to compare LDF. And that's what we're doing right here. What we're seeing is that the molar mass increases, the number of electrons increases, both of them do. What I'm trying to say here is that as this molar mass increases, as the LDF increase, so do the properties on the previous pages. They increase as well. So molar mass increases. London dispersion forces, LDF increase. Boiling point increases. And I'm going ahead and write boiling point there because it says it right here. I typically will refer to the boiling point as T sub B, the temperature. And this is pretty cool because just by looking at the species, we can make predictions about the properties such as the boiling point. And that's what a lot of chemistry is really about. Look at the chemistry, look at the bonding, or in this case, just the number of electrons, and predict something about its behavior when it boils. And something that we didn't really talk about, but I do want to say, so there's no bonding in these. Atoms are by definition nonpolar. So I don't think I said that before, but there's no bonds to be polar. Atoms are nonpolar, so all nonpolar. We have talked about this though. Alkanes are nonpolar as well because they contain only carbons and hydrogens. In fact, last chapter we had a rule of thumb that said anything with only carbons and hydrogens is nonpolar, therefore nonpolar. And what we're showing here is molar mass and boiling point, and we're finding a linear relationship between the two. It's not necessarily linear, and it's not 100% linear. It is sort of curving over there. But the idea here is that as molar mass increases, London dispersion forces increase, and boiling point increases. So same thing, now with molecules. So even though they're the weakest, they do, on a per atom basis or on a per interaction basis, get enough of them together, and your boiling point increases. Boiling point for nonane up to above 140 degrees Celsius. Questions about that? For molecules with the same molar mass, the shape of the molecule matters. This is N-pentane, one of the isomers of C5H12. And this one, 1, 2, 3, 4, 5 carbons in a row. Neopentane, well, neopentane, that was the isomer that looked like a plus sign, although there were various ways to draw it. First thing I'm going to point out is that while their molar mass is exactly the same, their boiling points are not. This one has a higher boiling point. Therefore, this one has larger intermolecular forces. Higher boiling point, larger intermolecular forces, even though they have the same molar mass. And it turns out that from one molecule to another, let's remember, intermolecular forces are one molecule to another, one atom to another. In order to interact, they have to literally interact. Two molecules of N-pentane will have a larger area of interaction. As denoted in red. These two, I mean, you can think of it as they just can't get as close. They can't overlap by as much as a smaller area of interaction. And I'm not sure exactly how we rationalize this otherwise, or like what's the best term. Like area of interaction, I don't know, that makes sense to me. Another word we use is surface area. I don't know. Let's go, like, sometimes I use area of interaction, sometimes I use surface area. Either way. But here's what you need to know about LDF. They get bigger as the molar mass gets bigger. When the molar mass is the same, think about area of interaction. And now we're getting into the details of LDF, London Dispersion Forces. If the molar masses are different, don't tell me surface area. Nobody cares. It was not the right answer because molar mass is a bigger trend. Question, which substance has the higher boiling point? Y. So A, butane, B, octane. How many people think A? How many people think B? Excellent. What would be the reason why?
Higher LDF.
It does have higher LDF, but what about it?
The molecule is larger.
Larger molecule, so you can either say larger molecule or higher molar mass, or more electrons. Leads to more LDF. So octane. So my thought flow is larger molar mass leads to larger LDF, leads to higher boiling point. And something that's happening in the background here that will come up is, first off, both of these are nonpolar. So both only have LDF. It will become more complicated as we go through the other ones. Questions about that? Now, I would not give you names like this, but I would give you skeletal structures. Butane, but is 4 carbons, A and E is all connected by single bonds. 2-methylpropane. I could give you these two, and you'll see actually on homework for chapter 11, I'll give you skeletal structures like this, and you should be able to look at these two, count up the number of carbons, show that the number of carbons is the same. Because their number of carbons are the same, and they have, therefore, the same number of hydrogens, because they're connected by single bonds. Both of these will be C4H10. Nothing on my sleeve. Do you believe me that these have the same molar mass? How many people believe me? If you don't believe me, there's a way to check, which is you can either look at this carbon and say that has 3 more hydrogens, 2 hydrogens, 2 hydrogens, and 3 hydrogens. You can fill them in and do Lewis structures. There are ways to check. Because of course, on the third exam and or final, you'll want to be doing things like checking your answers should you have time. But it is true, both of these will have the same. They have 4 carbons, 10 hydrogens. So, same molar mass. According to what I just told you, this one has more area or larger area of interaction and larger LDF and higher boiling point. And it doesn't have to be that different. I mean, this is 25 degrees or so, but they will, this is is what I love about chemistry, by the way. This small structural change here and or here leads to measurable differences in properties. All right, let me write that out. So both C4H10, same molar mass. Larger area of interaction or surface area, either term is fine with me. Larger LDF, higher TB. Okay. And this is just all the non-polar compounds, which tend to be a lot of organic type compounds, carbons, hydrogens. Good. All right, so now it's on to dipole forces. All particles have dispersion forces, true. Polar molecules also have dipole forces. Picture and description of dipole forces for two molecules of acetone. Well, here's one molecule of acetone. Sort of drawn on its side. That's its skeletal structure. We could draw its Lewis structure as well. Lewis structures have all bonds, all pairs of electrons, so I had to jog my memory and make sure I put the pairs of electrons on the oxygen. Quick check-in. This carbon right here, what is its hybridization? sp3. It has 4 electron groups. Good. This carbon here, somebody else, what is its hybridization?
sp2.
It is sp2. Very good. All that stuff will come into play now because we need to know the shapes around each of these, because that's going to help us determine whether something's polar or non-polar now. Right? So that's why we've been building on this. Okay. Any questions about these pictures? Then the next thing is going to be to show you that these have dipole forces, and that this is a polar molecule. I was working with somebody on homework 10, and they asked me something like, basically, if there's an oxygen in it, is it going to be polar? Almost always. And so we're going to focus on this carbon-oxygen bond as being the polar one. There are carbon-hydrogen bonds over here. Most of those dipoles are going to cancel out, though, although there is a slight non-cancellation there, but this is the main dipole. Dipole forces say that the partial negative portion of one is attracted to the partial positive of the other. And there are a couple different ways to show that, but my idea here is the negative portion of one dipole is close to the positive portion of another. And there's, again, a couple different ways to do that, any of which are fun. If you were writing an English sentence about this, you would say, the partial negative on one dipole is attracted to the partial positive of another dipole. These are permanent dipoles. These are not those instantaneous ones before. That's why these are going to be larger intermolecular forces than dispersion forces. What we say about polar molecules is that for acetone, the molecules have, so acetone molecules have LDF. In addition, they have dipole-dipole forces. And one thing I find helpful, and so I'm going to do it, is whatever the largest intermolecular force something has, that's what I'm calling the dominant intermolecular force. So for acetone, dipole-dipole forces are the dominant intermolecular force. Where dominant for me just means the largest one that is like available to us. Okay, I guess one other thing I'll have to point out to you is, so far, we're talking about two molecules that are exactly the same interacting together. At some point, we'll talk about molecules that are different interacting, but so far, these are two of the same molecules. So the intermolecular forces are related to the pure substance properties. And just to be clear, when I say pure substance properties, like if I took a container of acetone, pure liquid, I could get its boiling point. Okay? Now, if I mix that acetone with water, then it's not pure. Then I've got water and acetone interacting, and that's not pure. So that's not what I'm talking about right now. We will talk about it. I don't know if that, but we'll see. Any questions about this? Okay, well, the take-home message is now we know enough chemistry to start understanding the properties of materials, including boiling points and things like that. So the effect of dipole-dipole forces on the melting and boiling points of substances. So these two substances have exactly the same molar mass. Oh, well, 4/100ths of a gram difference. So I'm going to call that same molar mass. Which means they have the same or very similar LDF. Because everybody has LDF. They're very democratic And then we look at the boiling points and the melting points, and we can see that formaldehyde, here a substance that has a dipole, has dipole-dipole forces, much larger boiling point. And this is lovely because we can see what effect this dipole has, or dipoles in general, but this type of dipole as well. So, formaldehyde, CH2O, also has dipole-dipole forces, which significantly raise TB and TF. And I put the ... there because we could make similar statements for the other properties that were on that or second page of the notes for chapter 11. But I know boiling points and melting points are usually the easiest to access. Any questions about this? You good? Dipole-dipole forces increase as the dipole moment increases. And for this, I want to make sure I get it correct, which means I have to find my notes. Mu is the dipole moment. And dipole moment is going to equal to partial charge times the distance of separation. And, but we won't be doing dipole moments, so then if your question is why do I bring it up? Because it's useful to know about in the long run. Shortcut way to estimate dipole-dipole forces is going to be larger differences in electronegativity. Where delta En is the difference in electronegativity, larger delta En lead to larger dipole-dipole forces. And what you have to know for the exam. You have to be able to look at those two molecules, tell me a couple things about them, and this is a good time to go over those couple things. First off, HCl and HF, both of these have hydrogen covalently bonded to a halogen. And beyond that, it is useful to know that hydrogen is always covalently bonded to something. Hydrogen is always covalently bonded to something. And I'm not going to write this, but this is a common student mistake. The common student mistake is thinking that because way back in chapter 4 we wrote H+, that hydrogen can be ionic. Hydrogen is never ionic. That's the thing to remember. Chemistry is like an onion. There are layers of understanding. And way back in chapter 4, it was useful to think about hydrogen being a strong acid and producing H+. Now it is useful to know that hydrogen is always covalently bonded, which means it never has ion-ion forces, as we will see. All right. So both of these have dipole-dipole. Let's say this. Both of these, well, everything. Everything has LDF, so both of these have LDF. Both of these have dipole-dipole forces. Both have LDF, both have dipole-dipole. HF has a larger delta En, therefore HF has a larger IMF. HF has larger delta En, larger IMF. And therefore a larger boiling point, freezing point. Question, Leo?
So, does HF fall under like the hydrogen bonding category because it's one of like the...
Oh, shoot. I'm sorry, it does. That makes this a bad example. Can I backtrack for a minute? Okay. So, because I didn't want to introduce hydrogen bonding, I mean, maybe it's perfect, and yet totally confusing. Let me think about this for a second. Dipole-dipole forces. Do you remember what I said about hydrogen bonding and its relationship to dipole-dipole forces last time? It's just a stronger form of dipole-dipole forces. And so from that perspective, it's like I'm leading into my own argument here. But on the exam, which it says what you have to know for the exam, you'll see cases in which there are two substances. They both have as their strongest or dominant intermolecular force dipole-dipole forces, in which case that's not true for this one. So, darn. Is it okay if I rework this example? I apologize. I know that's terrible. Let's just call it HBr though. It's still a halogen, so everything works. Hydrogen always covalently bonded to something, still true. Both have LDF, both have dipole-dipole, but now HCl has the larger delta En. I'm sorry about that. I don't want to introduce hydrogen bonding. I got a little carried away, a little excited. But it's a great question to ask, Leo, and thank you for asking it. But we're doing them next, but you need to know how to answer this problem strictly in terms of dipole-dipole. So thank you for catching that, by the way. And I know, I hope I didn't lose too many people. Other questions? Good. Emilio?
So we're just looking at like the negativity to see which one's more like larger?
Yes. So And what we can say is that as you go down, electronegativity decreases. And you'll actually, on the exam, have the electronegativity scores for the halogens, oxygen, nitrogen, carbon, and hydrogen. So you have the trends based on the shape of the periodic table, but you also have the scores themselves. So you'll be able to evaluate what is the difference in electronegativity for each of these. And you would find, let's see, so 2.1 for hydrogen. .8, I believe, for bromine. Yeah, that should be right. And so larger difference in electronegativity leads to larger dipole forces. Let's see, good question. But what we're doing is, we're developing a process for doing intermolecular forces by looking at the molecule, being able to understand whether it's polar or nonpolar. Then once it's polar, you can look at the difference in electronegativity to determine which is the higher boiling point. If they're nonpolar, you look at molar, so you say it's only LDF. You look at molar mass. If the molar mass is the same, then you look at shape. So yeah, there's a system under here somewhere that we're working on. Good. Any other questions? Good. All right. Now, which has the higher boiling point? Again, I won't give you these names. On the exam, I'll actually give you the either Lewis structure or skeletal structure. And let's start with this one. So 1,2-difluoroethene. We'll start with the F, that's 2 carbons. Ene means there's a double bond between them. 1,2 means that on one of the 1 carbon and the 2 carbon, there's a fluorine each. And cis means that they're both on the same side. Again, you don't have to know nomenclature, but we are starting to introduce organic nomenclature here. Trans means that, that cis and trans deal with the positions of the fluorines. Now we can apply our process a little bit. Our process goes like this. Polar or nonpolar, well, one of these is polar and one of these is nonpolar. Which one's polar? The one on the left or the one on the right? I heard the one on the right, I heard the one on the left. Which one is polar?
The left one?
Well, let's talk about that. Because I know this is still all new, but our process for determining polarity is draw it in its correct shape. From there, draw dipole arrows for each bond. Not that you don't have to draw one for the carbon-carbon bond, because those have the same 2 atoms. We draw dipoles facing the more electronegative element. And then the question becomes, which of these has the dipoles that exactly cancel each other, and which one doesn't? Because the ones where the dipoles exactly cancel is nonpolar. I would suggest to you that since these 2 dipoles are in exactly opposite directions, and some instructors just have you ignore CH dipoles, that's fine too. And then you look at these 2 dipoles, these are real, They are in exactly opposite directions. However you do it, all of these dipoles cancel. Which is tricky, I know, but all dipoles cancel. Non-polar. Right? And one thing I didn't mention that is underneath all this, by the way, and which will change when we get down here, is we have to, I'm going to throw in the fact this is a double bond. Double bonds are rigid, meaning they cannot rotate. These dipoles are locked into place. Okay. And the case, right, so what happens in this chapter is, just like previous chapters, I'm going to show you every single case there is for how to do polar, how to do non-polar, how to do all these comparisons. And we're getting pretty tricky, by the way. All right. These dipoles don't cancel. In fact, you can see generally the dipoles are going up. And on homework 10, there's a couple questions that ask you to describe and or draw the dipoles. The drawing for this one, try again, would go up. Right, this is what's called the molecular dipole. Because the left and right portions cancel, but the up and up portions add. All right, so polar. As dipole forces. Has stronger intermolecular forces, stronger IMF, has higher boiling point. That's the level of analysis for this. Questions about this? Okay. Let's go on to the next one then. This one's going to be 1,2-difluoroethane, F, 2 carbons connected by a single bond. One, 2 means that one of the fluorines is on the one carbon and the 2 carbon or the other one has another fluorine. Those are both F's, not weird P's. All right. One of these is polar, one of these is non-polar. Let's do the analysis. I'll guide you through it. So, single bond can rotate. So, when I've drawn these two fluorines as up, those fluorines can rotate. So the fluorines are not locked in position. No, I've drawn, well, I haven't drawn Lewis structures. Let me make them Lewis structures by adding all the electrons to them. Otherwise, I don't know what those things are. Because they weren't shapes either. Next step, this carbon, what is its electron geometry?
Oh, tetrahedral.
It is tetrahedral. 1, 2, 3, 4 electron groups. That is always tetrahedral. Bond angle is 109.5. Same thing with this carbon. These carbons are the same as well. I'm going to redraw this one in an attempt to show you why this one is nonpolar. Okay? I would normally do it down here if I was doing your notes, but since I have a little more space up here, I'm going to put it up here. That's a double tetrahedral there, which I cannot ask you to draw. But once you've gotten it, because it has an out wedge on each carbon, it is true that as you go from F to C to C to F, at least in the configuration I've drawn it, they are all planar. This hydrogen here is coming out, the other one's going back. However, this single bond rotates, and it is now time for interpretive dance for this molecule. So here's the two carbons right here, and then here's the dipoles. Here's the dipoles. Wait a minute, I can do opposite way too. And over milliseconds, over nanoseconds, the dipoles on average cancel out. So it is the rotation about this bond that means the one dipole makes a cone, the other dipole on average makes a cone that cancels out. It's a pretty tricky example, but it is true. So, as these two dipoles rotate, on average they cancel out. As the carbon-fluorine dipoles rotate, on average they cancel out. Colon, conclusion, nonpolar. I don't care how you draw this one. I don't care how it rotates. These two dipoles, all right, will never exactly cancel. This is a polar molecule. Therefore, it has larger dipole-dipole forces and higher boiling point. Any questions about that? All right. Now, in the background for both of these examples, you'll know that both of these had the exact same molar mass. So the LDF were the same for this, so we didn't have to worry about it. Both of these have the exact same molar mass, so the LDF, again, we didn't have to worry about it. All right, Finally, hydrogen bonding. When a small, very electronegative atom, nitrogen, oxygen, or fluorine only, is covalently bonded to hydrogen, it strongly pulls the bonding electrons toward itself to become a relatively large partial negative charge. Because hydrogen has no other electrons, when its electron is pulled away, the nucleus becomes deshielded, exposing the hydrogen proton to become a relatively large partial positive charge. Still just large dipole-dipole forces. The attraction between the partial negative on NO or F and the partial positive on H is a hydrogen bond, a relatively strong version of dipole-dipole forces. Each pair of non-bonding electrons on the NO or F atom can attract an H. N usually has one pair of non-bonding electrons, one hydrogen bond. O usually has two pairs, two hydrogen bonds. F usually has three pairs of non-bonding electrons, three hydrogen. Well, am I cut and pasting here? Two hydrogen bonds, three hydrogen bonds. Is a hydrogen bond a true bond like ionic or covalent bonding? A. No. And it's here where I'd like to just bring up the ability of rational adults to agree and disagree. Because I was just having a conversation with my good friend and biologist, Paul DeGennaro, who teaches A&P here. Great guy. Would he call a hydrogen bond a bond? Probably. That's okay. We can agree to disagree. Right? Right? We're all adults. We have different opinions. Even chemists and biologists. So, strengths of the types of bonds. Ionic. Well, ionic bonds are characterized by crystal lattice energies. And if you think of the crystal lattice energies that you've seen in some of the examples from Chapter 9, and you'll see them again in Chapter 11, they are typically they're typically minus 1,000. That just means, the minus means there's an attraction there, or greater. That's their order of magnitude, which means approximately how many zeros are out there. Covalent bonds are typified by bond dissociation energies, which most of them are minus 300 to minus 900 kilojoules per mole. Strength of hydrogen bond. Minus 2 to 20 kilojoules per mole. So it is at least an order of magnitude smaller than the other ones. And although I should say that hydrogen bonds are bigger than the other intermolecular forces, dipole forces, and LDF, typically. So, and that's just to give you an idea of their size. And the minus signs, again, just mean we're all talking forces of attraction. Any questions about that? Pictures of hydrogen bonds. Well, there's two main types of questions I can ask you about hydrogen bonds. One is, draw all the hydrogen bonds that can form with one water molecule to other water molecules. And this is a pure substance type question. only water molecules. So think boiling point, freezing point, all those properties that are on the second page of the handout. Those are the pure substance properties. And even before I draw the picture, let me draw the distinction between here we go, acetone and acetone, also a pure substance. Hopefully on the next slide. There we go. Acetone with water molecules. That's the distinction I'm trying to draw. Because there are two different types of molecules present, this is going to be more related to solubility of acetone in water. Right? And the solubility comes up because you're interested in how one thing interacts with another. That's going to determine how things dissolve. But we have two cases of pure substances over here. All right, now on an exam, sometimes when I show you this picture, I will draw you a molecule, and sometimes I just draw one of them big. And then I allow you to draw other water molecules around it to show the hydrogen bonds. For water, hydrogen bonding with other water molecules, I would expect you to do the following. For each H, orient an O from water with one of its pairs of electrons towards the H. Okay? And it's here where I waver. Some semesters, that's the only thing I draw. Some semesters, I draw boop, 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 little sets of dashes there to show the hydrogen bond. Either way is fine with me. I worry about drawing those dashes that you'll think there's a bond there. But I also worry that when you get to your biology classes and they draw those lines, you won't have seen them before. So that's why I worry. Anyway, either way is fine with me. Let's take a vote. Would you rather I draw those dashes or not? Who would rather I draw those dashes? Who would rather I not draw them? Fair enough. The non-dashes have it, although you can still draw them. One hydrogen bond. Because that's all a hydrogen bond is the alignment of the two dipoles. This is partially positive, this is partially negative. You do draw the electrons closest to the hydrogen. Fair enough. I'll do the same thing down here. So. And then there are the pairs of electrons on oxygen. Which I draw hydrogen closest to. And I still have one more to do. Because your picture of a hydrogen bond has an O on one molecule and an H on another molecule close together with its pair of electrons in it. That's what hydrogen bonds look like in this class. They can have the dashes or not, but now I will ask, are there any questions about this picture? Okay then. So can acetone form hydrogen bonds with other acetone molecules? Well, let me draw an acetone molecule. Here's an acetone molecule. And the answer is going to be no. An acetone molecule cannot hydrogen bond with another acetone molecule because you need two things to make a hydrogen bond. You need to have an O with a pair of electrons, check. You need to have an H covalently bonded to O, N, or F. The only H's I visualize in acetone are bonded to carbon. Not going to form a hydrogen bond. Not a very polar bond. So, oh, my no is gone here. I could have used it again. No, it cannot, because acetone does not contain a hydrogen covalently bonded to oxygen, nitrogen, or fluorine. No, acetone does not contain a hydrogen covalently bonded to O, N, or. There are two things you need for a hydrogen bond. On one of the molecules, there must be an O with a pair of electrons. On the other molecule, there must be an H covalently bonded to O, N, or F. And I know I sort of whizzed through that last page with all the discussion of what they were because it was all printed for me. But these are the questions that you'll need to be able to answer for the exam. There's a third one that's up here. Can acetone form hydrogen bonds with water? The answer here is going to be yes. There's acetone. Acetone contains the O. Water contains the hydrogen covalently bonded to O. Now we can draw two hydrogen bonds there. Those are the types of questions. Check.
Can all the hydrogens on the two carbons in acetone get a hydrogen bond to the water as well, like oxygen and hydrogen?
They can't.
Okay.
So the basis of hydrogen bonding is that a hydrogen bond is basically the oxygen is a relatively large, part of a relatively large dipole. This is a relatively large dipole. The attraction between them creates the hydrogen bond.
Okay.
CH, they're almost the same electronegativity. There's really very little dipole there. I mean, and it's the same thing. I mean, there's a relatively large dipole here, but still much smaller than if this were an O in water. So this cannot be part of hydrogen bonding. The CH cannot either. It's a good question to ask because oftentimes, I don't know about oftentimes, but on a regular basis, people get to the third exam and the final, and I show them CHs, and they draw hydrogen bonds to them. And so that here I am telling you, that's not where hydrogen bonds form. Yeah, good question.